I don't really need these, but. Okay, so here, reminder of possibly bad title. All right, so basically, it's going to be very picture-y today, and like just tell you about this cool problem. It's very like hands-on that I got like super into. All right, that's kind of the idea here. Also, thanks for having me here. I was forgetting to say thank you, and this is really fun to be here. All right, anyways, so the whole time X is going to be a smooth, orientable four manifold. Pretty much like all I care about in life. All right, so smooth. I'll say it's oriented already. Four manifold. Okay, so it doesn't necessarily have to be like closed or compact or anything, I guess. Just like is what it is. Okay, and inside of X, I want to look at two spheres. So I'll have two spheres. I'll call them S and T for now. And they are smoothly embedded in X, first of all, so they look nice. And also they're homotopic to one another. Okay, so fine. They're like closely related two spheres. And I want to assume kind of one more condition about them for the rest of the talk as well. And that's that they have a common dual. So what I mean by that, I'll draw you sort of a picture for the definition as well. So you have your two spheres, S and T, sitting inside of X, smoothly embedded. And then you have another two sphere, so a third guy. That's called the common dual, so it's also embedded smoothly. It intersects both S and T, as suggested by this picture, in a single point transversely. And then the only additional requirement about this two sphere is that it has a trivial normal bundle. So, you can take it and sort of push it off of itself so that it doesn't intersect itself. So that's kind of critical property of this two sphere also. All right. So what this is kind of supposed to remind you of at this point, I guess, and we'll kind of maybe just like mention this like three-dimensional analogy to this situation like a few times just to like keep you on board, is like when you're in S1 cross S2 and you look at S1 cross point in there, there's like that two sphere S2 cross point, which kind of satisfies like the same characteristics here. So it intersects S1 cross point in a single point, and then it also has this like parallel push off that doesn't intersect itself. So it has kind of the same property. So that's what you should be like thinking of in the back of your mind. All right. So in keeping with that analogy, there's this theorem, which I will star. So this is due to Dave, goodbye, from last year. I'm writing Dave instead of goodbye. All right, so this is basically it's this like concept of, so in S1 cross S2 there's like the light bulb theorem. So this is saying if you have anything that's homotopic to S1 cross point, so it's like, going around, it's like nodding or whatever in S1 cross S2, and it intersects that two sphere S2 cross point in like a single point, then you can isotop it to just like the standard S1 cross point. So you can do that sort of by like sweeping across that like kind of dual two sphere to the curve. Okay, so first he kind of proved something so that's in S1 cross S2, so you're in 3D, and if you want to do something in 4D, then it makes sense to sort of go to S2 cross S2, right? So that seems like reasonable. But in fact, you can do this in manifolds like other than S2 cross S2 if you're kind of in this like starting setup. So you have two spheres, they're homotopic. You want to know if they're isotopic, and you know that they have this like nice common dual sitting there, then in fact you can kind of like play around with the homotopy that you have between them and come up with an isotopy. It's not necessarily like a deformation of it or anything, but it's like you produce this isotopy. So that's kind of amazing and what he proved last year. Okay, so let me just write that. So again, it's in more general four manifolds, so maybe the most intuitive like jump is to S2 cross S2, but in fact, as long as the ambient manifold has fundamental group with no two torsion in it, then the two spheres, set up like this again, S and T, are smoothly isotopic to one another. All right, so that's pretty nice because we get from homotopy to smooth isotopy. So that's like a big kind of simplification or whatever. All right, so here's kind of the situation in 4D, which, I don't know, I had to draw a chart for myself and it like soon became this like web of like entangled relationships. So I'm gonna draw it for you. All right, so let's see. So it's weird, so again, I'm saying like smoothly isotopic, like emphasizing the smoothly portion of that statement, because in 4D, things are like a little nuts. So first of all, like the smooth category and the topological category are not the same thing there. So in 3D, you know, when you talk about like a topological manifold or smooth manifold, it doesn't really matter like where you're living. But in 4D, it like very much matters because there's manifolds that are called exotic, which are homeomorphic to one another but not diffeomorphic. So first of all, like there's a big difference there just like the ambient, like the actual like 4 manifolds you're looking at. But even in the same smooth 4 manifold, so you're in the same smooth thing, you have smoothly embedded spheres or surfaces. They can be topologically isotopic to one another, but not smoothly isotopic to one another. So even though they're like living in the same like smooth space. Okay, so there's like all these differences. So you have to like really pay attention to like what adjective I'm putting before isotopic here. Okay, so that's kind of what this diagram is going to illustrate. There's a lot of kind of like complicated relationships here. Okay, so homotopy is kind of like the simplest equivalence between spheres. I'm thinking of spheres right now, but some of these things apply to surfaces as well. So you can, you know, ask them to be homotopic to one another. Okay, and then of course maybe the other two kind of obvious things are topological isotopy. So you can ask them to be topologically isotopic, or you can ask them to be smoothly isotopic, so I'm gonna write diff for like differentiable, all right? So these are like my 3 little like main prongs right now that I wanna think about. Okay, so obviously if they're topologically isotopic, they're homotopic. If they're smoothly isotopic, they're homotopic, and then if I forget the kind of smooth part, I get a topological isotopy from a smooth isotopy. Okay, so I have a nice little triangle happening. So going this way, so suppose I have things that are homotopic and I want a topological isotopy. Well, there's some times that I can do this, so I didn't really know how to denote this, so I put a little dotted line, because it's like, if I'm in a nice enough situation, this is sometimes a thing that you get. So for instance, this is due to probably a few people, but in particular, like Nathan Snookjian wrote a paper, like 2013, or I don't know, somewhere around there. So like if you're in a simply connected 4 manifold, it needs to be closed, and your surface, this allowed to be a surface, not just a sphere. They're homotopic of the same genus, and like they have a simply connected complement, or even a complement whose fundamental group is like finite cyclic or something like that. Then you can get, from them just being homologous actually, you can get a topological isotopy. So this is kind of like in special cases you can go this way, but here you're living in like, first of all, you're restricting to like simply connected closed manifolds, so that's like big restriction, and then you have this like big restriction on the fundamental group of the complement of the surface as well. So this is like very specific situation. And then going this way, of course, I start out with things that are homotopic and I want a smooth isotopy, so even stronger. Well, that you can do in this situation up here because of Dave's theorem. So this is by theorem star. So in particular, what you need is for them to have this like common dual, which in some sense is kind of rare because it's like really nice, like it's embedded and it has like, you know, trivial normal bundle, all of this. Okay, so sometimes you can go from homotopy to topological isotopy. Sometimes you can go from homotopy to smooth isotopy if you're in a nice enough situation. So this direction I kind of have clued you in now is kind of, you can do it sometimes I suppose, but in general, there's a lot of counterexamples to this. So there's a lot of 2 spheres that are topologically isotopic that are not smoothly isotopic. So I'm gonna put an arrow this way because like the non-dotted is meant to be like in general, this is false, sort of. Okay, and then these are like when you can kind of find situations in which it's implied. Okay, so why do I know kind of this direction? Well, it actually follows from like another little like area in here. So I'm going to call 2 spheres smoothly equivalent if there is a diffeomorphism of the like ambient manifold they're sitting in that's taking one 2 sphere to the other 2 sphere. So actually, there's a lot of examples of topological, or sorry, 2 spheres that are topologically isotopic for which there is no such diffeomorphism. So I kind of know that this is false. So this you can come up, it's like a 2-step process sort of, because first you come up with these 2 spheres, basically using, by Donaldson you sort of like by Donaldson's work, you know there's like, exotic four manifolds, and then you kind of have to use Wall also to like come up with these two spheres to begin with in like the same smooth four manifolds. And then, so you kind of know from the work of those two people from the 80s that like these two spheres that you come up with are not smoothly equivalent in this sense. And then you also have to show, of course, that they're topologically isotopic to one another. And so that you can use work of like Quinn and Perron, which is also like from the 80s. So like this is false has been known like for a while at this point, and there have been like examples out there. So anyways, so if, so these examples here, where they're topologically isotopic but not smoothly equivalent, so there's no diffeomorphism carrying one to the other. Of course, these examples are also not smoothly isotopic to one another, because I could take that smooth isotopy and then look at the very end of it, and that would give me a smooth map carrying one to the other. Okay, so because smooth isotopy implies smoothly equivalent, of course, if I don't have this, I'm not going to have this. Okay, so these examples, by the way, where they're topologically isotopic but not smoothly equivalent, there's examples even with simply connected closed four manifolds. So relatively simple. So examples with pi1 of the manifold equal to 1. Okay, good. So my question that I kind of want to focus on, so this is like why I got it. Well, first, his paper is wonderful. You should all go out and read it. But at kind of like, this two torsion thing was like kind of bothersome, because it was like, it like seems so nice, you like have such like a clean statement, and then it's like there's this like pesky two torsion issue like hanging around. Like, what if there is two torsion? Then what happens is like the obvious question. Okay, so the question, a Q, just so everybody knows like what it is, I guess. All right, so does the theorem star hold in general? So in particular, like I said, if there's two torsion in the fundamental group. All right, so in fact, the answer is no. So basically today I want to show you just like a little construction of a four manifold with these two spheres. So let me just write it and then I'll say it maybe. Okay, so there exists examples of four manifolds, so still calling them X, with their fundamental group isomorphic to 2, so certainly there's two torsion there, such that the two spheres S and T, so again, it's the same setup as on that board, it's always going to be that way, such that these two spheres are not even, so they're homotopic by virtue of that board, but they're not even topologically isotopic to one another, so certainly not smoothly isotopic. Okay, so they arise in sort of like a cutesy way, and so I'll tell you about them. All right, that's kind of what I wanted to say. Oh yeah, so first of all, not only does there like exist an X for which this works, but there's infinitely many. And also you can choose it, so I mean at first like the most obvious picture was sort of a bounded manifold, but you can also come up with closed examples. So closed or bounded manifolds this works in. All right, so in fact, kind of what happens here is it gives examples of kind of the reverse direction of this not being true, which is also weird. So it makes this diagram like potentially more confusing. So the examples we come up with, and I'll like mention this again and kind of like tell you a little bit why, but these two spheres are smoothly equivalent, so there's a diffeomorphism. And in the bounded case, it restricts the identity on the boundary, carrying one sphere to the other. So they're smoothly equivalent, but like the theorem says, they're not topologically isotopic. So here, this is false, and these examples happen where pi1, these examples in particular have pi1 z2. So not simply connected like this way examples, but at least there are definitely examples this way when the fundamental group is non-trivial. Okay, cool. So I'm going to give you a little picture idea of like what's going on there and like what weird stuff's happening. Okay. Are there questions? Yeah? Yes. Mm-hmm. Yeah, so there's just single intersection point. That's very important. Okay, so let's see. First I want to tell you the four manifold. So we're going to talk about the compact case first, since it's just the smallest one that I have in mind. Okay, so what does it look like? Well, first I'm going to just describe it more like hands-on, and then I'll draw you like a nice curvy calculus picture if you like that kind of thing, so you can like go either way with this. So first I want to take a solid torus and cross it with the interpole. So here it is in my picture. And of course, that's fundamental group Z, and I'm aiming for fundamental group Z2. So I'm going to first kind of start out with the manifold Maggie was talking about the other day. So it's just like take this two handle up here, and I'll draw it like this. So it's a disk crossed with a disk to make it four-dimensional. And I'm going to glue it in. I'll try and use a color here too. So I'll glue it in along the S1 cross S2 on the boundary to this a neighborhood of this curve here that wraps twice around the solid torus. Okay. And again, I have like an integer's worth of ways to do this depending on how many times I want to like spin the disks as I go around the S1 direction. So this is already like there's like choices involved here, and like it's fine no matter which sort of integer you choose as your framing. Okay, so now, good, this is the right fundamental group, so that's like a positive step in the right direction, but it doesn't really have like the two spheres that I need hanging around in it. So I want to add some more two handles, keeping the fundamental group the same, so I don't want to kill the generator, so that I can see both some kind of two spheres, S and T, sitting in there, and also I can see like a common dual for them both. Okay, so the first thing I want to do is get like the spheres S and T kind of set up for myself. So add another two handle sort of on the bottom, and I'm going to attach it, again, along the same exact curve that wraps twice around. So it's just the copy of this curve, but the guy living in like the lower solid torus here. Okay. And again, I can use any sort of integer framing that I'd like to like attach the two handle. So now there's this family of two spheres that may kind of like pop out to you from this picture. So I'll do yellow, which you probably can't even tell. All right, so there's the disk kind of going over the top two handle. There's the obvious disk going over the bottom two handle. Right? And then they need to be connected by an annulus that kind of goes through like kind of the S1 cross B3 in the middle. So what I can do, so I have a few choices here. So first, I can sort of look at the two sphere where this curve just kind of like drops down with the product, so there's no twisting as you go. So that I'm going to denote like that, so it just drops straight down. And this two sphere I'll call sigma sub 0. Okay, so no twisting. Or what I can do is as I descend through the I factor, I can just like twist an integer number of times. So I'll like land back on this curve at the bottom, but as I go, I've sort of twisted around. Okay, so that I'll denote like this as I'm doing like two twists and then landing on the bottom curve to form my annulus. So if I'm doing n twists, let me label that two sphere sigma n. Okay, so like at first glance, I have this like integer family of spheres sitting there in my four manifold. So that's a good start, and maybe like two of them can be like my S and T potentially. All right, so now of course I still need a common dual. And there's not one that's like easily suggested to me in any sense. And so rather than like really think critically about it, I just want to like plop one on so I have it there. So what I can do is look at a little meridian to this curve up here where the top two handles attached. And I can just attach another two handle along that curve. So what that does for me, well, first of all, it does not impact the fundamental group, right? Because this curve here that I'm attaching the two handle along bounds this little disk that pierces the attaching curve in just one point. So this disk, because this disk exists, it's null homotopic, and so it doesn't impact fundamental group, fine, whatever. All right, so this disk, together with the disk going over the two handle I've just added, if I attach this two handle with the correct framing, I get a common dual for all of these two spheres, since there's only this one intersection point coming from this disk here, which intersects the two sphere like right here, sort of the bottom of this little disk on the top going over the two handle. Okay, good. So just add this on to my four manifold, and now I have a nice little common dual sitting there for like all of these two spheres. Okay, so I have all of them to sort of play with and find hopefully two that are not topologically isotopic to one another, which would be nice. Okay, so if you're in curvy calculus world and you want to draw this manifold, it's just a one handle, a two handle. So this is like the manifold Maggie drew for us yesterday, and then I want to add two more two handles to this. So I need kind of the one on the bottom, I suppose, and then I add the little dual here. So this guy has to have framing 0, but these two, you can really choose any integers for the framings that you want. And the diffeomorphism type of this manifold is determined by P, and also by Q mod 2, because I have this dual here. So, all right, so this is the 4 manifold, this compact 4 manifold that I'm living in right now. Okay, I don't even know. Right, okay, so now I will tell you 3 facts, apparently. I was like, what's next on my notes? It's kind of fun to try and remember it. Okay, so some of them you're just gonna have to like trust me, and then some of them you'll actually like kind of see like why later they're true. Okay, so first fact is this issue of the 2 spheres, the sigma n's, being smoothly equivalent that I was kind of referring to earlier. So there's a diffeomorphism taking one to the other. So let's see, I'll say there exists this pairwise diffeomorphism. So it's going from x sigma 0 to x with sigma n in it. Oops. And this is for all n. Okay, so you see like a stupid one initially, right? Because, where did my thing go? So you know, sigma 0 is dropping straight down and sigma n is twisting. So of course there's a diffeomorphism taking x to x, which sort of just twists this solid torus as you go along. But this does not clearly like restrict the identity map on the boundary, right? Like, or at least anything even like homotopic or isotopic to the identity map. So like sort of, I don't know, like not super exciting. But in fact, there's a diffeomorphism that restricts the identity on the boundary. Or I'll say fixing the boundary. Okay, so that's kind of interesting. Or if the boundary, or if there's no boundary, then obviously it's not an issue. But where this diffeomorphism comes from is the fact that there is this common dual in the first place, which is nice. So you can sort of like surger it out and use an argument, or using the Palace theorem, whatever, that says if you have 2 embeddings of 4 ball in my case, then they're isotopic to one another. Okay. So that's kind of where this comes from. Okay, so that was fact 1. Fact 2 is that, so I want to know kind of when these guys are homotopic to one another even, because, you know, I want these spheres to be homotopic. So it turns out that sigma n and sigma m are homotopic to one another, if and only if the subscripts are congruent mod 2, so if they're same parity. Okay, so we'll see a picture of why that's true if you can't already see it in a second. And then third fact is that, okay, so this is just kind of like surprising and like, I don't know. So the 2 spheres sigma n and sigma m are smoothly isotopic. At least when n and m are congruent in mod 4. Okay, so this fact, it doesn't follow from how this theorem stated, but from like the proof of Dave's theorem, if you actually like read through it, it's clear that sort of it implies that these two spheres are smoothly isotopic when their like indices are congruent mod 4. This is sort of, well, okay, so these 2 spheres in the first place, I mean, like, where did I did not like draw this manifold and then just like plop in these 2 spheres and like do things. It was like they came from this like particular like homotopy that was there between them, sort of. That was like kind of critical, and it shows up in Dave's proof a lot, sort of. And so the fact that there's this like specific homotopy between them, if you sort of do it 2 times, it takes you from like sigma 0 to sigma 2 or sigma 2 to sigma 4. So if you want to get from sigma 0 to sigma 4, you have to sort of like do it twice. And in that case, like Dave's like techniques can sort of deal with it and churn out an isotopy from it. But in the case when they only differ by 2, it's not clear that they're smoothly isotopic to one another from his theorem or from his proof. Okay, so really, there's not an integer's worth of 2 spheres here is the takeaway from that. There's really only 4 that I've drawn, because there's sigma 0, sigma 1, sigma 2, and sigma 3. And maybe there's actually only 2, but I don't really know. Well, okay, so it's, yeah, because of this, I know that, you know, sigma 0 is definitely not sigma 1 because they're not even homotopic to one another. Okay, so there's really at most 4 2 spheres here, and then at the least there's 2 of them. Okay, so now the task is kind of to figure out which of those, exactly how many there are. Okay, so to do this, I want to, instead of looking in X, I want to look at the twofold cover of X instead and look at some two spheres there. I don't really have a good system for this at all. Let's keep his theorem up there. Okay, so, I was gonna do it so that it was like above it on the board, but I'm not that cool. Okay, so we can all just imagine it's living above here. I had that thought and then just didn't do it. Okay, so, right, so X tilde, we'll draw the universal cover, it's gonna be twofold. So, again, like I'm gonna do it piece by piece because I like this picture just as like my mnemonic. So this guy gets covered by basically the same thing, but it's gonna wrap twice around it. So I have a solid torus in the middle, cross with I, and it sort of unwinds the generator of pi 1. So it's gonna wrap twice around here. So this green curve, or both of these green curves, they're gonna have two lifts upstairs, right? So they're gonna have, okay, so here's where I'm gonna say blue, but actually draw orange. All right. So it's gonna lift to two curves. This top one is gonna be like a hop flink, right? Because I have this twist happening here. So I'll see modulo like the crossings that I draw. I'm just gonna be sloppy. So I'll see these two components up here, right? And then the same thing's gonna happen when I lift this green curve, is I'll get like a red component and like a blue/orange component. Oops. Good. Okay, so likewise, each two handle lifts to two handles attached along these curves that I've drawn. So I have like two different like red two handles here, here, and then I have two different orange two handles here and here. And then my dual has two different lifts, so there's gonna be like one on the left, one on the right, sort of, so. All right, here's my little guys, and they're attached along one component and then along the other component of the hop link. Okay, beautiful. So now I can look at sort of the lifts of these two spheres that I have, right? So each two sphere is gonna have two different lifts. So there's sort of gonna be like one of each color here. So one living like on each side of the picture. So I'm gonna have like an orange guy here. And then, you know, depending on how many times I see the twist here, if I have n twists downstairs, there's gonna be n over 2 twists upstairs. Oh, sorry, I did this wrong. Okay. Step by step, everyone. Okay, so let's first just take these up here. So I have a pink side and I have an orange side. Okay, so what's gonna happen, so, okay, I have the lifts of like the top disk kind of up here and here. And then as you lift the annulus, depending on how many times, you're gonna see like n over 2 twists. So there's sort of two different kinds of lifts you can see. You can either see a lift where it sort of stays to one side. So I have this sphere that's all orange and this sphere that's all red. Or, you know, if n is odd, then when I divide by 2, I'm gonna have some, I'm gonna, you know, not have like an integer's worth, like an integer twist here. So it's gonna kind of lift to things that like switch sides, right? So if I have like one whole twist here, I'm just gonna get a half twist upstairs. So that kind of should justify to you why when n is odd versus even, these two spheres are not homotopic to one another, since they lift to two spheres that are not even homologous to one another upstairs. Okay, so let's just, for sake of me drawing this picture, think about sigma 0 and sigma 2, so the even guys. So, you know, sigma 0 is gonna lift to two spheres where it really just like drops straight down in the annulus. And then sigma 2 is going to drop to ones that kind of twist like one full time around. Okay, so again, orange kind of stays on the orange side and pink stays on the pink side, but they do this little like twisting in the middle. Okay, so depending on what n is, what my sigma n is, I'm going to call this sigma n sub r for red, and then sigma n, I'm going to do b for orange. Okay, so good. Okay, so in particular, I kind of want to like localize like really like the difference between these two spheres, because like what's happening on these like top and bottom disks is not super exciting to me. So I want to like zoom in into like the difference between them. So I want to look at a little submanifold here, which is like really like the critical like difference between, is like I can look like add a little disk in the solid torus, and then cross it with I. So I'll get a 3-ball sitting inside my manifold X. Okay, so it looks like a little tin can sort of thing. And now I want to look at how, this union of spheres sort of like sits in this tin can when n is equal to 0 and when n is equal to 2. So I'm going to call this 3B. All right, so my little diagram for us is like, here's B, this disk cross I. So again, when I look at the lifts of sigma 0, so we'll call this, I'll just do this, we get it. Well, as I go down through the I factor, again, like these curves really aren't moving, so it's just this like straight down sort of thing. But if instead I look at the lift of sigma 2, then in the 3-ball, I see a tangle where there's just one full twist as it goes down. Okay. So again, this is like really like how these two things like differ from one another. Okay, so good. So now, okay, so first of all, we already know that sigma 0 and sigma 4 are smoothly isotopic even downstairs, right? But it turns out upstairs, there's also these kind of common duals hanging around upstairs that were the lift of the common dual from downstairs. And they kind of help you to ascertain that there is an isotopy upstairs taking the lifts of sigma 0, so this disjoint union of two spheres, to the lifts of sigma 2. So the two guys together, like the two spheres, are isotopic to the other pair of two spheres, smoothly isotopic. Okay, so I don't want to try and like obstruct a smooth isotopy between them because that's better fail because they are isotopic. Okay, so that's like not really the direction we're headed in. But instead what I want to say is that there's sort of no smooth isotopy between them. That's the lift of an isotopy downstairs because that's the isotopy I sort of want to bar. Okay, so that's where we're headed. Okay, so what I want to do is just consider any isotopy, fix an isotopy. And this isotopy at this point, if I want to show they're not, topologically isotopic, I work in the topological category and I am always like locally flat when I'm doing that. So fix an isotopy, I'll call it H, so it's going to be going from, again, the disjoint union, sigma 0, B, union. Oh, let's go from 2 to 0, actually. So the lift of sigma 2 is this disjoint union. And then I'm going to the lift of sigma 0. Okay, and then, I can kind of like look at the track or trace, whatever you call it, of this isotopy. All right, so what I'll do is just kind of look at it in like the region where B is, because that's sort of the most like interesting region to me to really look at. So I have this 3-ball B that we drew over there, and I can cross it with time and the isotopy. Okay, so I already drew, so let me just really quickly redraw kind of the beginning and end of that isotopy. I know I start at sigma 2, the lift of sigma 2, and I end at the lift of sigma 0. So over here, I just have this like boring 2 arcs, not twisting, and then over here I have this like slightly but not really more exciting tangle happening. Okay, and then, throughout I have, this 3-ball crossed with I, so really what I'm seeing here is a 4-ball. And I'm seeing, again, kind of the trace of this isotopy happening. So this is a 3-manifold, and this 4-manifold intersecting, so I should see, as long as I have some like assumptions on transversality, this like surface of intersection between them. So like generically on like a slice here, I'm going to see some sort of like crazy tangle happening. That's like the intersection of my surface with that slice. Okay, so here I have this like surface. Oh, here, let me just write time in isotopy. Okay, so I have this surface in B4, this 4-ball. And it has these red and blue components, or orange, whatever. Okay, so I'm going to call them alpha and beta. Okay, so these are disjointly embedded surfaces living in the 4-ball. So if I look on the boundary of this situation, I'm going to have this like red and blue link living in the 3-sphere, right? Okay, so let me draw that for you in a specific way. So first of all, I'm going to see sort of this 3 ball and this 3 ball definitely in this boundary S3. So I have the one on the left here, all right, and I see this tangle on the inside. And then I see this outer one sort of like out here filling in the rest, and so I see this tangle over there as well. So it's like not linked, okay. And then, you know, in between here I have an S2 cross I, which is like happening as I sort of like scan here along in the isotopy. And so I'm going to see here some sort of a tangle, right? But I kind of want to understand a little bit more about like the structure of this tangle, right? Because it's not just like any old tangle, it's like somehow a little bit special. And it's special because, so this 3-ball B like has a few restrictions with respect to how the isotopy is intersecting it, right? So the isotopy is like staying away from the boundary of my 4-manifold at least. And part of the boundary of this 3-ball is contained in the boundary of the 4-manifold. So there's some parts of the boundary that the isotopy can't touch. So let's look at it a little bit more. So I have my 3-ball here. And again, in my manifold, went the one under here, so just remember it in your brain. The only place sort of where the 2 handles that I added are attached are sort of, they intersect the boundary of the 3-ball in these 2 discs here. So the discs are part of the S1 cross D2, right, that the 2 handles attached along. And then likewise down here, there are these 2 discs where the attaching region of the 2 handle intersects the boundary of this 3-ball. Okay, so there's these 2 discs that are really on the interior, like the interior of those discs are in the interior of the 4-manifold. The rest of the boundary of this 3-ball is in the boundary of the 4-manifold, so the isotopy can't touch it. So these discs, you know, they're like staying here throughout this whole like time interval. So I see them sort of here, these little discs crossed with I in my picture of the boundary, right? And so, in fact, the tangle that I see that's happening in this S2 cross I region needs to really like live inside of these little regions here. Okay, so, you know, from here to here, they're going to be connected by some rectangle. It could be knotted. There could be other components. There doesn't have to be one component. There could even be like, you know, orange components in here. There's no reason it needs to have one color to it, right? But again, they all kind of stay within this little like tube area. Okay, and the same here and here and here. And I'll see like this little, it'll be another tangle, so that it'll be an orange with like 2 endpoints. And then there's going to be some other sort of link happening inside, whatever it might be. Okay, so that's coming from the intersection of the isotopy kind of with the boundary of this 3-ball. Okay, good. So now the point is, so I want to, again, not necessarily like this is allowed to happen, right? H can exist. It's just an isotopy between the 2 things. But what I don't want it to be is a lift of an isotopy downstairs between like the 2 spheres that we started with. Okay, so kind of the fact here is that if the isotopy H does lift an isotopy from sigma 2 to sigma 0 in X, then the linking number between, okay, so here we have a link and it consists of the boundary of the red surface, so the alpha, and then there's the boundary of the blue surface, beta, right? So this is the, here, it's like a disjoint unit of these 2 things. So I can look at the linking number between like the red components of this link and the blue components of this link. And their linking number needs to be odd if H is really the lift of an isotopy downstairs. Okay. Right. However, that's like clearly a bad thing because I have these links and they're living in S3 and they're bounding these 2 disjoint surfaces that are living in the 4-ball, right? So their linking number better be 0 or else like I'm in trouble. Okay, so this gives me a contradiction, which is nice. So kind of the idea behind this is like I have this like single twist happening, so that's kind of contributed 1 to the linking number. And then what I can do is, if this is a lift, I can sort of use like the deck transformation of the cover to make sure that kind of these 2 little like mini tangles inside this S2 cross I have the same linking number as one another. and that these do also. So everything happening in this S2 cross I kind of gives it an even contribution to the total linking number of this link, and then I have nothing coming from the outside 3-ball and just 1 coming from the inside 3-ball. So I'm going to get an odd linking number in that case. Okay, great. So this is sort of like a little picture of the example. All right, so of course, I promised you in the theorem there's like infinitely many manifolds, and that they can be both closed and or bounded, depending on what you want. So, you know, the manifold we came up with, I said you could choose kind of whatever like framings P and Q to attach those manifolds with. There's already like infinitely many manifolds we've been talking about so far. But, you know, if you want something like a little cooler than that, maybe. So let's see. We can argue like a similar argument applies. In a few different cases. So, all right, first of all, I can look at my manifold X and I can connect sum it with like things. So for example, I could connect sum it with CP2 or CP2 bar. I could connect sum it with, you know, however many number of S2 cross S2s I'd like. Sort of the mantra here is anything, I can add as many 2 handles I'd like to this picture so long as they stay away from this 3-ball B, right? Because that was really the only thing we like super looked at. So as long as they sort of stay away from the 3-ball B, their attaching regions, it's like okay to attach it. So like, you know, here I'm just adding on these little unknots or a little hop link along which I'm attaching 2 handles. They can like definitely stay away from the 3-ball B, which is just basically like a co-core of, or a co-core of my 1 handle, kind of. Okay, so fine, in like any number of blowups you want or any number of stabilizations you want, you can produce similar examples of 2 spheres. Which is kind of weird because when you're in simply connected, like closed or something, usually like stabilizing the manifold like dissolves like weird activity. Although that usually happens when things are like topologically the same but smoothly different, and here we have they're not even topologically the same as one another. But anyway, it adds kind of like just a weird extra facet into fitting in context to things. What? Say it? No, I guess connecting some with anything would be okay. Because it's just connecting some, yeah. But like, yeah, I was just thinking more of like you could have any crazy 2 handle you want, but like still, yeah, just plop on anything and it should be okay. Yeah. Anyways, those are just what came to my mind, but yeah, fine. But anyways, so still compact in this case because X has boundary. So what I can do instead is like double it. So if I want a closed manifold, a similar will also work in the closed double. So here I take X downstairs and I have the 2 spheres sigma n living in X, and I can just flip it over and plop it back on itself. So I have negative X up here and X here. So I now have still Z2, because all I'm adding here, I have 1 and 2 handles down here, so I'm adding 2 and 3 up here, and the 2s are attached along null homotopic curves, so I'm fine. And yeah, you can also, so this argument for the closed double is a little bit different than kind of, the argument up here literally like just runs through in the exact same way. But here, when it's closed, there's sort of a different situation because now I can't like do the same thing like I just told you. There is no boundary of X when it's closed, and so I don't have this sort of nice like, you know, way to divide up the boundary of the 3-ball like I just did and like do anything with making these 2 equal or whatever. So that kind of like falls a little flat. So what you can do, I'll just tell you the idea very quickly for this. So, when it's closed, I mean, certainly you can make the isotopy disjoint from like a 4-ball, right? So like the 4 handle of the manifold. So really what you have to worry about, so you know, again, zoom into sort of the same 3-ball B. So you have, you know, X has like this 1 handle now sort of attached. So you see the 3-ball B living in there. And then you have, you know, 2 handles coming from the double, and then you also have like one 3 handle actually coming from the 1 handle flipped upside down. So that 3 handle is attached along S2 cross I, that's the attaching region there. So now when you're looking at the 3-ball B, you're gonna kind of see these regions living on the interior of the 4 manifold, but then also, so remove the 4 handle from the manifold. So you're in a bounded manifold now, but it just also happens to have 3 handles. So you see the attaching regions of the 3 handles of the manifold intersect the boundary of this 3-ball B in like little, like, you know, thickened curves. So the little annuli that are living in there. So in particular, so you know, I just literally drew it and doubled it and then saw what the attaching regions of the spheres were. And you can see that they intersect the boundary in like these little, just literally these 2 curves and then just like thickened because it's like the attaching region. All right. So that means now instead of living in this little area in S2 cross I, now my tangle in fact lives in this area together with, they're like these solid tori, I guess, living inside of here. So I'll squeeze one of them into the picture. So it's like this annulus crossed with I. So I'm also now allowed to have a tangle living there. So that's going to contribute to the linking number. So it's going to be however many times, you know, this link living in like this green solid torus can wind around any number of times. So that will certainly affect the linking number. And then also, you know, the individual components can just be linked with each other. So like the actual just linking number of like the stuff in this solid torus is going to affect the linking number of like the entire link. So those kind of 2 things you have to pay attention to in this case. So, but anyways, so once you sort of, again, it's sort of just like a process of like subdividing like what's happening on the inside of this S2 cross I, and then like paying attention to like how they're related. And again, coming up with the same contradiction that this linking number better be odd. Anyway, okay, that's really all I have for you. I don't know what time it is. So there's 2. Well, okay, if in this whole family, really, so thinking there's like an integer's worth, that's false. So there's at most 4, and now I there's 2 like that are there's 2 different like representatives in terms of like topological isotopy class. Even, what, say again?
So if you fix the homotopic,
yeah.
How many?
So, let's see. There's 2. There's just like, so for like sigma 0, for instance, you look at so everything, homotopic is just sigma 0 and sigma 2. That's it. And then those things are, I mean, they're just themselves, but they're not topologically isotopic, and those are like the only 2 choices there. So yeah, given homotopic classes, there's 2 different like smooth representatives. At least in this family, like maybe there's some other one that like we're not seeing in this like picture, yeah. Like yeah, so maybe there's a 3rd one like hanging out. I don't really know. No, actually no, because your theorem should probably say there's not, because I think there should only be 2, because kind of your theorem, because it is talking about like the number of crossed, like you look, okay, there's only 2. Here's why. So these 2 spheres, so again, I chose them because there's this very specific homotopy between them. So in Dave's paper, during the homotopy, you know, you're doing finger moves and Whitney moves. That's like this classic thing, right? So you know, finger moves are what they are, but then in terms of Whitney moves, once you've done all these finger moves, there's like 2 kind of distinct types of Whitney moves that you can do that, I don't know, I call in my head like crossed or uncrossed. But it sort of has to do with like the initial sheets that are kind of induced by the finger moves, and then you have to see if like the Whitney move is sort of pairing points with like similar sheets or opposite kind of sheets. Anyways, so there's these 2 types. So with Dave's theorem, you can kind of rephrase like, you know, his like the proof, what he's actually proving is that if you are in like any 4 manifold and you have a homotopy between 2 spheres with like an even number of crossed Whitney moves that don't like correspond, okay, an even number of crossed Whitney moves corresponding to to elements of order 2. So that's like, you have to pay attention to the ones that correspond to elements of order 2, then they'll be smoothly isotopic to one another, sort of. So in this manifold, I chose this homotopy between them so that it had an odd number of Whitney moves corresponding to this single element of order 2. And so if you have any two-sphere that's homotopic to these guys, to this pair of two spheres, well, it's going to be smoothly isotopic by your theorem to one of them, because there's going to be a homotopy to one of them with an even number of cross-Whitney moves corresponding to that single element of order 2. So yeah, there should only be two things, I think. Anyways. Yeah. Yeah, like, I think so I think, like, just the fact that it was, you could definitely do the same sort of thing for stuff that's not just Z2, first of all. Like, you could add on different one handles that won't affect it, stuff like that. And then, yeah, I think you could probably, do something. Yeah, there's definitely, like, this will generalize to other stuff. I just haven't really, like, thought there yet or done that. I don't know.